Thank you for coming out. My name is Jeff Baker. I'm an electrical engineer with March Consulting Associates here in Saskatoon, and this is the third in the series of lectures titled Safety for Electrical Engineers. What we're looking at today is kind of just a final overview of safety if you're visiting site as an engineer and your responsibility as an engineer. This first slide is looking at just hazard identification. Before visiting site, you want to review the work to be done, have a plan in hand, and an idea of what kind of safety issues you may encounter. Many sites actually require you to do a safety plan before even getting there or when you get there, which just identifies some of the hazards that you may see when you're at site, which would be like a tripping hazard, or if you're walking up stairs and you're working at heights, even though there's railings and it's not truly heights, there's still concern there, and there's moving machines around you. So you write those things down, really just showing that you're aware of potential hazards, and you generally get a tour of the site so you can see. If you're doing a design for site, you get a tour from someone experienced who works at site to show you around and make sure you're familiar with the hazards that may be present, so that when you're putting your design together, you can incorporate that knowledge into your design. And then when you get back to the office, you can develop a plan to control the hazards. So if you know that a piece of equipment has to be suspended 20 feet in the air, and as an electrical engineer, we're not equipped to design structural for that, support system for it, but you are aware that it's going to be up at height, so now you need to contact a structural engineer to plan for that, support that weight. This is a short little video. Hopefully the audio comes through.
If we were to cross the road here, the hazard is being hit by a moving vehicle. Part of doing a hazard identification is looking at the potential consequence. In this case, it could be a serious injury or even a fatality.
But we're on a country road. I mean, the chances of being hit look pretty slim.
Right. That's part of the risk assessment. Because the traffic flow is very minimal, the risk is low.
Whoa! But if we were trying to cross the road here, the hazard is much worse.
Nope.
Nope.
Nope. The hazard is the same, and so is the potential consequence of a fatality. It's the risk that's changed. It's now higher because the traffic flow is much heavier.
Okay. The hazard is the thing or condition that can hurt us. In this case, the vehicles. And the risk is the likelihood that the hazard will cause injury or disease. So, what does that have to do with the regulation?
Hazards arise out of the work environment and work tasks. And until you know what the hazards are, you can't determine the risks. In the workplace, you have to identify all the potential hazards and then assess the risk they pose. For example, if you were pulling a heavy box off a high shelf, what are the hazards?
Well, if the box was stacked poorly, it could fall on you.
Or you might strain your back lifting the box. Or if you tried to climb up, you might fall.
Wow, I didn't realize moving one box could involve so many hazards.
Right, there are often many hazards associated with a single task, and we need to assess the risk for each of them.
Gotta unmute my mic after watching that high quality acting. But the intent of that video is just stressing the difference between the hazard and the risk, and something that comes into play as engineers. And we don't typically do this as a formal analysis on our projects, but you have to identify, if you're installing a new or designing a new motor control center to go into a mine site, you have to be aware of the fact that there's hazards inherent in electrical distribution, and at the same time be aware of the risks. If you've got a enclosed piece of equipment, the risk of it having a fault in the short term should be very low if you've designed it correctly with enough capacity to interrupt the power and enough operating safety. But you have to be aware of that and assess it as you prepare your design to make sure that any hazards are mitigated and the risk of them occurring is much lower. And now just some electrical lab safety rules. So first one being an electrician, this is speaking about, really, as engineers, I said it before and I will always say it, we're not qualified to get anywhere close to the power at any of these sites, any of the client sites. If you're working for a mine and you're at the site, working in and around electrical equipment, we are observers. We analyze the situation, we prepare designs, we work with the electricians. The electricians are trained to work with the power, work with the equipment. Engineers are not. Keep your hands away from it. Let the electricians do what they're trained to do. They're well trained, especially the ones at the mine sites. They only hire journey persons with experience at high voltage. These are not people right out of school. These are well trained, experienced professionals. Trust them. Trust them, work with them. They may even give you advice to improve your design with safety improvements or reliability improvements. Listen to them. They know what they're talking about, and you may come up with reasons why what they're suggesting doesn't work, but at least assess it and discuss it with them, because these people know what they're doing. The next one being water. This should be obvious to any electrical engineer. Water and electricity do not mix. If you have water in the vicinity of a power distribution, make sure that you're isolated. The power distribution is isolated from the water, and if there's any contact point that can't be isolated, like a plug-in, put protection on it. Your typical protection would be a ground fault circuit interrupter, GFCI. It's required by code when you're within a few feet of a water source. And at the mine sites, if you're working with, if there's generally higher power, and typically in any other process areas, they just require a GFCI even if there's no water directly around it, because upset conditions happen, water spills happen, and they would just rather err on the side of caution. The next one is disconnect. Always disconnect all equipment before cleaning or adjusting it. This we've talked about before, lockout, tagout. Make sure the power is off. Make sure that if the system can't be safely designed to be worked on without a disconnect, make sure that those warnings are put on the label on the door. Make sure it's very clear what people are working with. The fire extinguisher, you'll see fire extinguishers in every electrical room. It's required by code, and typically we put one in by each door, so that if, regardless of where an electrician is working in the room, if a fire happens, they're close to a fire extinguisher. But you can't use a standard water fire extinguisher on a door or on an electrical fire, because it's just going to make the problem worse. So you need one that's rated for electrical fires, which ABC fire extinguisher is. ABC is the different ratings of fire extinguisher. And then ground. You have to have a clean connection to earth. It's explained in the electrical code very clearly how that needs to be developed. If you've ever been around something as straightforward as a home construction, you'll see bare copper conductor tossed in the trench around the outside of the building. It doesn't encircle the building, but it goes for a good 10 feet near the incoming service, and then that ground is brought in and grounded to a ground bar inside of your electrical panel in every home. At mine sites, because there's a lot more power, we typically have a larger ground grid at the substation, and then that ground is carried forward to make sure that all site is at the same ground potential. At any of the large pieces of equipment, like a large transformer, a large motor control center, switchgear, you'll actually ground both ends of the equipment with two grounds. That way, if there's any problem in the inside of that complex system, you've still got a ground, because if you lose that ground, you can get a potential difference between earth, the ground that somebody may be standing on the floor, and the enclosure itself. So if an electrician walks up just to open the door, that potential difference can be enough to shock them and injure them. So we want to make sure any of the big equipment is double grounded, just as a protective measure. And then the warning signs. Tingle would be if somebody's feeling a small tingle when working with a piece of equipment. Typically at a mine site, the power levels are quite high, so they bypass the tingle stage. But if they're working with the low voltage, there is potential to hit that stage before, just as a notification point, I suppose. But if somebody's feeling that, they're probably not wearing their proper PPE, because you should be protected at all times, and the power should be off. The next one is frayed, dry, cracked extension cords. Normally at mine sites, they're not using extension cords unless there's construction going on. But anytime they are, as part of the safety checks during the start of the workday, the electricians, the workers in the area, should be inspecting all their equipment to make sure it's safe. Electrical cords are designed to be very flexible. They're designed to be temporary, and unfortunately that means they get stepped on, they get wheels of equipment run over them. They can certainly get damaged over time, and they need to be inspected before use to make sure they're safe. A grounded plug with the third prong cut off. Believe I have one. Nope, I don't. I didn't do it that way with my test rig. That would mean let's see if I can get this into frame at least. So on your typical plug, you've got your line and neutral, your hot and neutral connections, and then you've got this longer stub, and that's your ground stub. If you have a GFCI, it's going to trip out if you've got a fault between line to ground, and that's the intent of it, is to protect your system. But what some electricians do, and these are not the ones who would work at a mine site because they'll be fired immediately, they'll actually cut the ground off. That way the GFCI doesn't trigger and they don't get their work interrupted. It's a very unsafe practice because you're bypassing your safety system. If it's ever identified when you're working at site, or when you're working at all, throw out that cord, get rid of it, or report it to the safety officer, whatever needs to be done. It is, anytime you're bypassing your safety equipment, you're increasing the risk of a hazard occurring, and we don't want that, because that's when people get hurt. With the next one being, next item, smoke, sparks, spilled liquid, erratic operation. Anytime you see smoke coming out of any piece of equipment, there should be concern, unless it's a controlled fire as part of a process. Ignore that one. It's got a chimney, it's dealt with. But if you see any sparks or smoke coming out of controls or electrical equipment, I would suggest getting out of the area and alerting someone, finding a disconnect to shut the power off. Something bad is going to happen. Pull the fire alarm, make sure people are aware. When there's smoke, there's fire. When there's fire, especially with electrical equipment, it's going to cause additional faults, and things are only going to get worse. So if you spot any of these problems with electrical equipment in your lab, stop using it and call an electrician for repairs. Be aware of your surroundings, be aware of your equipment, and stay safe. Alright, so housekeeping. Just some general recommendations for safety. Prevent slips, trips, and falls. Maintain fire safety. Appropriate storage of tools and equipment. In the labs, where tools go is all labeled. Any of the larger equipment has serial numbers and is marked on the shelves where it needs to be placed. And then contain potentially hazardous materials and equipment. If you're working with anything that is hazardous, be safe, follow the safety rules. There's TAs in the labs to help and provide the training required. Hierarchy of safety controls. We covered this a bit in previous lectures, but this is very important in any work that engineers do, both when you're in the lab working or if you're doing designs in the field, to keep this in mind for people who will be working in and around your equipment. With any hazard, the first step to safety is to eliminate the hazard altogether. If you're preparing a design, you want to think through how that equipment is going to be used, and if you can, just eliminate the hazard from your design. That's not always possible. If you're dealing with 230,000 volts, it's inherently dangerous. So the next thing you want to look at is substituting the hazard with a safer alternative. Again, you need 230,000 volts, so you're not going to be able to substitute it, but in some instances you can. If you've got a machine that can operate at a higher voltage, lower current, or a lower voltage, higher current, you need to consider which installation is going to provide a better safety, and that's going to depend on the distribution of power available to you, the enclosures available to contain the risk, and the amount of fault energy at each one of those distributing voltages. So you have to analyze it and look at the safest installation, and then isolate that hazard. So a great example is that 230,000 volts. You want that high enough above any work plane such that nobody is at risk. In the first lecture, I talked about the example of somebody standing on an elevated platform to operate the controls, and as long as they were lower than a certain height and not putting their arms in the air, they were safe and isolated from the power. Well, that's really not the right way to do things. Move that control by design down to the ground level so that they don't have to go up on an elevated platform. Alternatively, lift the poles higher so that the voltage is much further away from any risk. Just keep that hazard away from anyone that could be harmed. And then using engineering controls to reduce the risk. That would be something like a GFCI. If you know that there's no way to remove the water from being close to a power outlet, then that power outlet should have a GFCI on it, so that if there's a water spill that sprays onto some electrical equipment and causes a fault, the power is going to be disconnected, interrupted, and that safety issue is mitigated. So that would be an engineering control example. It's inherent in the design that the power is going to be disconnected before anybody is injured, and when that power is disconnected, anybody working in the area identifies that that's a problem and needs to mitigate that issue before returning power. Next one would be administrative controls. An administrative control would be a procedure that do not open this cabinet until the power is disconnected upstream. Administrative controls are good because workers know if they violate them and are caught, they'll be fired, but they're also a bit of a risk because if they don't get caught and they get away with it, they can get injured. And it certainly happens where you get people working at site who take a shortcut and potentially injure themselves. And the last one is personal protective equipment. Something we do as engineers is called an arc flash study. You'll analyze the amount of energy potential inside of an enclosure so that if somebody's working in there, they know that they could be exposed to a certain amount of calories, it's called, which is just a certain amount of energy that could be blasting. And based on that, they know how much protective equipment to wear. The default being cotton clothing head to toe that's rated typically 8 to 10 calories, gloves, eye protection, hard hat. But if the amount of calories goes up, they can get all the way up to a bunny suit, we call it, or as a slang, I suppose. But it's basically full coverage. It's sweaty, it's uncomfortable to be in a long period of time, but it protects them, and it's important that they know how much risk is there, so that they can wear the proper PPE. So any electrical engineer should be very familiar with these, but just a quick rundown. We've got voltage, electrical potential between 2 points, at or below 600 volts is low voltage per the electrical code. Resistance is opposition to the current flow. Current is the rate of charge past a point, the element that induces injury. And wattage is unit of power that quantifies the rate of energy transfer. And then kilowatt hour, power delivered over time. Current needs potential and time to do damage. Current interrupts the heart function but requires voltage to move and time to damage. Mild shock can occur at less than 5 milliamps. The GFCIs operate at very low levels, and that's why they're protective for people. Your standard breaker is a overload protection. It's designed to protect equipment, protect cables. It's not designed to protect people. People are protected by things like a AFCI that we talked about a couple of lectures ago. Goes in a bedroom to protect against arcs that can generate fires, whereas a GFCI is protecting against a ground fault. Water shorts from ground to line to ground, or somebody touches line while they're touching ground and gets shock. GFCI protects a person in that situation. And then injury potential. So experienced workers, this is maybe counterintuitive to what you would expect, but experienced electrical workers have the highest percentage of electrocutions in the workplace, and new workers have the least likelihood of percentage of electrocutions in the workplace. The reason that is a new worker to a site, new person in electrical work has a healthy fear of the electricity, a healthy dose of concern for their safety. Whereas an experienced electrical worker, they've got 20 years on the job, they know what they're doing, they've done it this way all their career. They're not afraid. And when you're not afraid, you tend to take risks. Or when you've always done it this way, you tend to take those risks and keep doing it that way. A good story of this is a friend of mine used to be the head electrical engineer at one of the mine sites around here, and he was telling me that one of the hardest things he had when he first started was working with an electrician who had been there for 30 years, knew the site inside and out. So he's the guy you trust when you have questions about how site works, because he knows it. But when he went to him and said, I need you to go do this work in this equipment, here's the PPE you need to wear, here's the procedure that we've worked through, the electrician told him, tough luck, I've done this before, I don't need that equipment, I don't need to wear that PPE. Well, that's not really an option, and it's hard to explain to someone who's stubborn and set in their ways that this is what needs to be done for safety. I know you got away with it in the past, you got lucky, no damage happened, you were safe, but now, at that time, we weren't aware of the risk. Arc flash is a relatively new thing in the last 20 years, as far as being able to properly assess the risk, doing the calculations, analyzing it, doing testing to understand the amount of damage potential there. So electricians who were trained in the old ways may not be doing things correct to protect themselves. And as much as they're very skilled and they're probably very capable of getting away with it again, we would rather they do it with the extra personal protective equipment and be safe so that they go home at night than see them get injured and potentially die on the job, because it may tick them off to put that extra gear on, but at least they're alive. So they can get upset all they want, but put the gear on or you're going home without a job, because there's no other option here. And ventricular fibrillation is a condition that interferes with normal heart rhythm and may cause blood circulation to cease. Primary point of damage from electrical injuries. If you've ever been shocked by even 120 volt, the breaker, if it's not on a GFCI and you touch between ground and line with your fingers, you could get hit with up to, about anywhere from 12 to 15 amps at 120 volt before that breaker trips. But that path of current is going across your fingers. So it hurts and it sucks. It usually tells you that you shut off the wrong breaker and you should have used a tool to check and make sure that that power was off before working, but at least you're not dead. Now, if you reached in with two hands, you've got two hands across the system, and electricians will call it their two-hand rule. Work with one hand, not two, and the reason being If you go with two hands, now that path between the fault goes from up your hand, across your chest, and out the other arm. Well, right in the center of your chest is your heart, and your heart is a muscle run by electrical impulses. And if you get interference by an outside electrical source, it's going to cause that heart to operate in strange rhythms, and that's where you end up with ventricular fibrillation, and it can get bad enough to kill you. Okay, now this is going to be interesting because I have never done this on stream, obviously, since this is the first time I've recorded it on stream. Oh boy, that was a mess. Hang on. This is the little enclosure I built. And what I'm unraveling is a GFCI outlet on an extension cord, so that I've got some control over power on this system. Alright, I got the power turned off and the GFCI tripped. Now we can plug in, knowing that there is no power. That guy's not fitting in that one. Downside to the GFCI outlet is that it is really tight for space. Alright. Maybe the box wasn't the greatest idea ever, but too late to worry about it now. And now the little hot dog. So the purpose of this is to show what current actually does, what happens when somebody is electrocuted. Got my disgusting uncooked hot dog. We'll put it between line, ooh, don't want him sticking out, and neutral. A napkin, because that is gross. Now, the reason for the GFCI is to, actually before I turn this on, PPE is important. I got my gloves. They're PPE rated, or they're ARC rated gloves. They're electrician's gloves. They're made of leather, so they've got some protection. And the reason for having the GFCI is to show, before I talked about people cutting that ground connection. Well, here we've got line and neutral going across the hot dog, and then I've got this little bare copper wire sticking out the bottom. That's actually the ground connection. And I'll show you that with this ground disconnected, that hot dog is just going to keep burning. The GFCI is never going to trip. So let's turn this on. Okay, so it's running. Right now there's electricity flowing across the length of the hot dog, and it's actually burning it. And as you'll notice, you can't actually see the burn. So a typical electrical injury, there's, from the outside of the injury, there's only an entry wound and an exit wound. You won't see on the outside any actual damage, but what's actually happening is that power is flowing right through the center of this hot dog and burning it on the inside, which is the same thing that happens to a person. They're going to get that flow going on the inside of their body across organs, causing major damage, hence the ventricular fibrillation at the heart, or it can damage liver. Like, any part of your body can be burned and damaged by electrical flow, and ultimately you'd like to avoid that because it can be a problem long term. Even if you survive a low amount of current across your body today, over time that may have damaged cells and may cause you other problems as a result. That's why it's so very important to be safe. I suppose in the YouTube video I can speed this up a bit, but I want it to really burn. I can see some smoke. You probably can't see it on camera, but there's some smoke coming out the one end over here. It might actually be showing up. It's coming out pretty good. Now, if we trigger the GFCI, it actually shut off instantly. You'll see the lights are off on the GFCI now. Power is now disconnected. Just to be sure, I'm going to flip the switch. And then let's pull this stinky guy out. You can see the only injury to the hot dog is on the entrance and the exit wounds. But if we cut him open, we'll see actual burn inside of the hot dog. There's no more power here, so I suppose I don't need my protection. I always stop the experiment too soon. It's not even burned that bad. Yeah, it's really just burned at the entry and exits here. You can see all the black. That would be typical like inside of a human body if you were to get burned. That's effectively what's happening. That's where your organs get injuries, and if you're dealing with higher power, that injury is going to happen much quicker. You know, you're talking seconds as opposed to... Uh-oh, that's gross. I'll have to clean that out later. But you're talking seconds instead of multiple minutes or longer. So yeah, it's something to... Alright, that's awesome. Let's see if I can shrink this back up. Actually, switch back to presentation. Turn off the wide cam. And go to this one. There. Okay. So now I have a mess of a burnt hot dog on the floor. That'll be for cleaning up after. But yeah, that's why it's important to make sure that that ground is connected to a GFCI. When that ground is disconnected, the GFCI is defeated, you've bypassed your safety, and you run the risk of being burned in the same way that hot dog was burned. And even that small amount of energy is enough to injure your heart or internal organs. So keep that in mind anytime you're working in and around electricity. Be safe, wear your PPE, make sure that as an engineer you're not actually getting anywhere close to the power. Let the electricians do their job, trust them to give you advice with your designs. A lot of times clients will have their electricians review your design before you seal it and issue it IFC, issued for construction, so that they can take a look at it and put themselves in the mindset of working on that piece of equipment, and they can identify additional concerns or improvements to your design to improve their safety once it's all installed. Take their advice, listen to them. They tend to have good advice since they know what they're doing. They've done it for long enough. But yeah, that concludes the safety series for electrical engineers.